Welcome to the introductory webinar for ECOFusion, a new and exciting proposal that has great promise for meeting the world's energy needs through clean, safe, and cheap nuclear power. This webinar will cover how ECOFusion is designed to work, looking at the chief technical hurdles, as well as the breakthroughs that have been made which will allow this exciting technology to become a reality. A quick look at the scientific credentials will be mentioned, followed by an overview of the ECOFusion size and cost. The ECOFusion development plan will be discussed, and the webinar will wrap up with some concluding remarks. ECOFusion is a new approach toward achieving fusion that uses colliding beams. The idea is to use the well-known science of particle beam storage rings and apply that science to fusion energy generation. The particle beams will be accelerated to the ideal energy for fusion to occur, and then focused and steered into collision to produce the fusion reactions. The particles that do not fuse or are not lost in rare collisions are recycled around the ring for repeated attempts at fusion, enabling the system to supply the input energy only once. Here we see an animation of the ECOFusion device. Deuterons, indicated in blue, are sent in from a deuteron ion source into the storage rings on the far ends of this device. The deuterons then cycle around the device, and each time they come around, more deuterons are added, developing a very large current within the ECOFusion system. In the middle ring, tritons, shown in yellow, are put into their ring. Again, the tritons cycle around the ring with more tritons being added on each pass throughout the device. In this way, both the deuterium and triton currents become very large indeed. In the system, there are overlapping regions where the beams can collide with one another. Focusing elements within those regions focus the beams to very small spot sizes, maximizing the amount of fusion energy that comes out of the device. It may seem that the ECOFusion idea is rather obvious, and the question naturally arises as to why this hasn't already been done. The answer is that there are typically two technical hurdles that need to be overcome to make ECOFusion a reality. First, the ECOFusion design calls for beam currents of 10,000 amperes, which is extremely high by particle storage ring standards. Forming such beams is extremely difficult, and such beams are usually unstable. Second, extremely high levels of neutralization must be achieved in order for ECOFusion to operate, with the electron system requiring a neutralization of 99.9999%. For these reasons, colliding beam fusion approaches have generally been abandoned at a very early stage. The advances of ECOFusion entail delving deeper into each of these issues in order to provide the needed solutions. For each of the two main technical hurdles, the ECOFusion design has proposed a breakthrough technological solution. First, to achieve the needed high currents of deuterium and tritium nuclei, high current electron cooling is proposed. It is well known that electron cooling will allow for stacking of beams. This is the process of continually adding new beam on top of a stored beam. This will allow large currents to be built up gradually. It is also well known that electron cooling will prevent beam instabilities by controlling particle trajectories on each turn. The technology of electron cooling for ECOFusion presently has one patent pending, and two are about to be submitted. A second breakthrough is in the area of high levels of neutralization. Here, an esoteric technology demonstrated in electron cooling collectors has been extended to enable high levels of neutralization throughout an entire beam. A three-dimensional ion trap is formed to trap neutralizing ions. For this breakthrough technology, a patent has already been issued. The next few slides will briefly introduce each of these breakthrough technologies. Here we see the underlying mechanism of the electron cooling process, which is the first ECOFusion breakthrough. In 1956, Spitzer recognized that ions slow down in a free plasma of electrons. Basically, the positively charged ion attracts the electrons due to their opposite charge. the energy gained by the electrons is lost by the ion until it has the same energy as the electrons. 10 years after Spitzer's work, Butker realized that an electron beam is simply a moving, free plasma of electrons. He realized that if an electron beam was formed at the ideal velocity wanted for the ions, that the ions would obtain their ideal velocity. An ECOFusion breakthrough is the realization that the electron beam will damp away any random kicks that the ions get as they go around the ring. Since it is these random kicks that lead to instabilities, high current electron cooling can cure beam instabilities. Secondly, ions injected with a small angle will have that angle eliminated by the electrons, and this is what allows high currents to be obtained in ECOFusion. We can keep adding small current on top of a large stored current to get the high currents desired. The second breakthrough that will allow ECOFusion to operate comes in the area of extremely high neutralization of particle beams. Here we see a diagram from the utility patent granted on the invention. In a normal electron beam, the electron beam is formed by heating a metal that frees electrons from the metal surface. These electrons are then accelerated to form the beam. The breakthrough was a realization that a final deceleration of the electrons would provide an electric field that would force any ions back into the central beam region. By accelerating the electrons at the end of the device, an electric field would exist that forced the ions back to the central region from that end as well. This would then cause the ions to travel back and forth between the ends of the system, neutralizing the electron beam space charge. However, the ions could conceivably escape sideways. In order to prevent the ions from escaping on the sides of the device, magnetic fields are formed using wires in solenoids and toroids that keep the ions trapped transversely to their motion. Therefore, the ions are trapped in all three dimensions. The overall system should achieve the desired levels of neutralization, since it is known from tokamaks that plasmas can achieve very high levels of neutralization. Tokamaks require millions of amperes, while the ECOFusion will require only 10,000 amperes to operate. At this point in the ECOFusion overview, it is relevant to look at some underlying credentials. I am Dr. Delbert Larson, and I am the originator of ECOFusion. I earned a PhD in accelerator physics from the University of Wisconsin back in 1986. My thesis project involved the design and construction of a 2.5 million volt electrostatic accelerator that was intended for the electron cooling of antiprotons at Fermi National Laboratory. I then held several positions in various universities and national labs, which led to my appointment as the lead accelerator physicist on Fermilab's positron emission tomography accelerator in the mid-1990s. During all of my career, I continued to develop computational tools to design accelerator systems, and in every case where the designs were actually built, the devices worked in excellent agreement with their designs. This success surprised many in the field, since in each case the design techniques were quite different than what was typically done. Throughout the time I was designing accelerators, I would occasionally look at using accelerators as a possible solution to the problem of fusion energy production. And a few years after the end of the PET project, I had come up with an idea called ECOFusion. I then devoted 6 years to ECOFusion until I finally arrived at a design that I believe will work. ECOFusion has been presented many times to scientific audiences, with the first presentation being given at a 2007 International Fusion Conference held in Washington, D.C. After that, ECOFusion has been presented to scientists in small and large groups, including colloquia at Fermilab and the University of Texas at Arlington. 2 patents have been issued for technologies that underlie ECOFusion. An important aspect of ECOFusion is that it is a modular approach toward fusion energy generation. There are many advantages resulting from the fact that ECOFusion is a modular approach. First, laboratory work can be done on a full-scale module with no need to worry about uncertainties of scaling the device up for a future reactor. Second, in a working reactor, if it is desired to power up or power down, one could simply turn on or off individual units. Third, in a working reactor, regular maintenance can be scheduled by periodically removing and replacing only a portion of the reactor. Lastly, the modularity means that working reactors can be made that have a range of output power, from tens of kilowatts to gigawatts, depending on the need. As an exercise, it is interesting to calculate the size of a gigawatt power plant using ECOFusion. Each ECOFusion module is 1 meters high by 3 meters wide by 22 meters long, and each module has an output power of about 60 kilowatts in the present fully studied design. This would leave a 1 gigawatt power plant with a size similar to that of present coal-fired power plants. It might at first seem that ECOFusion will be prohibitively costly. After all, we are proposing using thousands of particle accelerators to build a gigawatt power plant, and the first prototype is predicted to cost around $15 million. However, it is important to realize that the $15 million is mostly salaries for scientists and engineers, and that the first one will be a one-off custom development. Eventually, the design will be consistent, and each module identical to the next, which will enable mass production of the units. And in mass production, costs are typically driven by materials costs. With design upgrades, it is already foreseen that each ECOFusion module could produce 300 kilowatts of output power. $300,000 can buy a lot of materials, which would enable ECOFusion units to be built for $1 a watt, which would be very cost competitive. And while ECOFusion will use permanent magnet materials which can be expensive, eventually the ECOFusion units will be recycled, lowering the costs still further. Lastly, since the fuel for ECOFusion can be found in water, there is practically a zero fuel cost. Therefore, in the long term, ECOFusion promises to be an extremely cheap source of power in addition to its other many advantages. The ECOFusion development plan has 4 main milestones going forward. First, we plan to demonstrate high current, low voltage electron beam operation in order to show that high levels of space charge neutralization can be achieved on a benchtop scale. This initial demonstration is achievable for about $50,000, and proposals have been submitted to pursue this work. Once the benchtop device has proven operational, we plan on working on a full-scale electron cooler, which is estimated to cost around $500,000. The final step in the experimental program is a full working prototype, which we expect to cost about $15 million to construct. Once the prototype is proven to work, ECOFusion will be ready for commercialization of the technology. Should this program be fully funded, it is expected that we should reach the commercialization point in less than 5 years. You have just seen how ECOFusion has great promise for the world. ECOFusion uses an inexpensive and inexhaustible fuel source, it produces no greenhouse gas emissions, and there is no direct production of nuclear waste. ECOFusion does not use nor produce weapons-grade fissile materials. ECOFusion is cost competitive in the long term, and a fully funded effort should result in fusion energy being available within 5 years. If you'd like more information, you can view the full scientific presentations at ecofusionpower.com. The presentations there are the same ones that have been given to various national labs, industries, and universities. If you'd like to help, please tell others about ECOFusion and refer them to ecofusionpower.com. Raising the visibility of the project can help to eventually find funding. Thank you.